This is a PRACE training portal video tutorial on process topologies in MPI. In this tutorial, we will present yet another convenient feature of the message passing interface paradigm, that of process topologies. MPI process topologies are constructs that provide a simple referencing scheme of MPI processes. MPI supports Cartesian and graph topologies. A process topology creates a new communicator which can be used as an argument in communication and other MPI routines requiring a communicator argument. By using this communicator, ranks can be referred to using their linear rank number, but through the use of Cartesian coordinates as well. MPI topologies are virtual, meaning that they are not necessarily related to the physical structure of the computer. In other words, process mapping onto the topologies is more natural only to the programmer. Process topologies will thus not bring performance benefits for all supercomputer architectures, but the main reason for the use is for code to become more compact and readable. In this tutorial, we will introduce how to generate Cartesian topologies. These are accomplished through the routine MPI card create. It requires 5 input arguments. The first is the communicator whose ranks we are going to reorder in a Cartesian grid. Second, we need to specify the dimension of the topology, that is 2 for a 2-dimensional grid, 3 for 3D, and so on. Then we need to provide an integer array of this dimension, providing the number of ranks in each dimension. The fourth argument specifies whether the grid is periodic or not for each of the dimensions. The last input argument is whether the MPI library is allowed to renumber the ranks for better performance. The output argument is a new communicator where we can refer to ranks with Cartesian coordinates. So how do we know the coordinate of an MPI rank? By using a routine MPI card calls, we can convert a linear rank number into a set of coordinates in a given Cartesian topology. We will have to input the dimension of the topology and get as output the coordinates of that particular rank. 2 numbers for a 2-dimensional grid, 3 for 3-dimensionals, and so on. The opposite of this is when we want to convert a given set of coordinates into a linear rank, which is achieved with the MPI card rank routine. As an example, let us reorder 16 MPI ranks into a 2-dimensional grid of 4x4 ranks. We first define an integer array containing the dimensions. Then we want this grid to be periodic. By calling the MPI card create, we get out a new communicator, com2d, in which we check out the rank and the corresponding rank. As you have likely figured out, this call will generate a grid like this, with a convenient coordinate notation available. Now, if I would like to send a message to the nearest neighbors, I don't have to compute a global index, but just send a message to both coordinates plus and minus 1. We will consider another related routine which is often used in conjunction with Cartesian topologies. The routine MPI card shift will identify the desired communication partner rank, very much like manually computing it from the coordinates. For each Cartesian dimensions, we can determine the ranks around the calling rank, provided as output arguments source and dest. We will need to specify in which axis we are operating on. 0, for example, refers to the y-axis and 1 to the x-axis in the 2-dimensional grid, as well as how many neighbors away. Displacement argument equal to 1 means the rank next to the calling rank, but it can also be greater than 1. The calling rank is an implicit input to the routine. If the Cartesian grid was periodic, and if the source and or destination for some rank would refer outside the grid, a special value MPI proc null would be returned. Let us try to illustrate the use of the MPI card shift within the topology we generated earlier. Now suppose that we wish to make a typical halo exchange communication scheme by sending the boundary data to the ghost regions in the nearest neighbors and at the same time receiving data to the ghost regions of a particular rank. By generating the Cartesian topology and finding the neighbors up, down, left and right of every task, we can write the whole Kähler exchange communication pattern with just 4 MPI send-receive calls, without any need for special treatments. So far so good. Please go through these examples and try them out yourself.